All right, so as we continue on the notes here for Chem 30, as we you guys worked on your worksheet there for basic atomic structure, let's keep talking about ions, and you can fill in the sheets that you have there. So ions are charged atoms as a result of an imbalance of protons and electrons. We talked about this last class. So an atom is always neutral. Okay, if you have a neutral calcium atom, and you look on the periodic table over there, calcium has 20 protons. And so if it's an atom, there's no charge, and it also has 20 electrons. Okay, we know that. If there's an imbalance in protons and electrons, the positive charge and the minus charge there, if there's an imbalance, then you have an ion, a charged ion. And calcium forms a 2+ ion. So it has a 2+ charge typically because it likes to lose 2 electrons. Okay? Now let me just go back, and I just want to take some time now to just explain why that is as we pass through these. Oh, I know what I got to do. Sorry. I'm going to go back to the notes. Okay, so here we go. This is from last day. And if we look carefully over here at calcium, there's calcium right here. And you see on your periodic table it has a 2+ there. Okay, that's the typical charge for a calcium ion. Now, why is that? From Physical Science 20, we talked about why atoms like to give up or accept extra electrons, and that's because of the outer shell of electrons. And the outer shell of electrons for this level right here contains 8 electrons. It's called an octet. Do you remember that word from last year? An octet of electrons. If an atom or an ion has a full octet of electrons, and we'll talk more about this when we talk about valence electrons coming soon, but if an atom, okay, does not have a full octet of electrons, it likes to either pick up the electrons needed to have a full outer shell, or it likes to get rid of its extra electrons so that it has a full outer shell. Okay, so just think about this. If our classroom, okay, if 2 people were missing, we would feel a little incomplete, right? We have some people missing. So when those 2 people come and make a full classroom, now our classroom is as it should be, right? If there's 2 extra people in here, let's say we have 2 elementary kids just kind of walking around, floating around in here, something's not right with our classroom, those 2 elementary kids would have to go to their classroom. They would have to leave. And this is the case with calcium. It's like it has 2 extra elementary kids, and it's just going to kick 2 of those out so that it has a full octet. It has the same number of electrons as argon. Okay? And the noble gases, we said, are noble because they don't like to react with any other elements, and they have a full octet of electrons. That's why they're satisfied. Okay? They don't need to pick up electrons from anybody else. They don't want to bond with anybody else to borrow their electrons. And they don't need to give up any electrons, so they don't want to bond anybody else with anybody else by giving up electrons and sharing them with them. They're just fine on their own. So calcium makes a 2+. Okay? So more on that later, but you see these charges, beryllium, in the same position in the periodic table. Magnesium, also the same position. Strontium, barium, radium. So they all have 2+ charges because they like to kick off 2 electrons to become like this noble gas that's near them. Okay? And over here, consequently, fluorine, chlorine, bromine, the halogens, they have a -1 charge because they have an outer shell that's not quite full. Okay, so for fluorine, right, if you look at this, it has 7 electrons in this outer level. And it would really like to have 8 because then it would be, sealed right up. And so it likes to pick up an extra electron. Okay, so that's why the charges are the way they are. Questions? Yep. So fluorine is negative, yeah, because it has 9 protons. That won't change, but on its outer shell it picks up an extra electron. So now it has 10 electrons, so 10 negatives and 9 positives. So overall, it's a -1 charge. Yes, and okay, so fluorine as an ion, fluorine -1, if it lost that electron, it would become neutral again. Yeah. yeah, but calcium as an atom, so let's say Ca, right, has 20 protons, 20 electrons. But it doesn't like to have 20 electrons. It only wants 18. So it gets rid of 2 electrons. And overall then it has 20 positive charges and only 18 negative, so it's plus 2 overall. Okay? Okay. Any other questions? Okay, that was a good question. Do you understand all that now? Okay. Okay, so let's go back to the notes here then. Just notice that if you write 2 plus or if you write plus 2, they're both acceptable ways of writing. It doesn't really matter. You'll see me probably do both actually. If something is a negative 1 though, we typically don't write the 1, just like a negative sign. Okay. All right, so next in your notes here, I want to talk about atomic mass units. Okay, and again, this is basic chemistry stuff. This is stuff that we have should have talked about in physics or physical science 20 that you may remember. But let's just go over it again. Protons in the atom, okay, have a mass, and the mass of each proton is 1 AMU. That's 1 atomic mass unit. Okay. It's not a gram, it's not an ounce, okay, it's not a picogram, it's just an atomic mass unit. Now, what does that actually mean? You know what, it's kind of all relative when we're talking about the atom, okay? A proton is 1 atomic mass unit. A neutron is 1 atomic mass unit as well. So the proton and the neutron have pretty much identical masses, okay? Now, we'll talk about what that is in grams. It's something extremely small, okay, grams, but if we're talking about just relative mass in the atom, protons and neutrons have the same mass. Electrons, okay, now this is where it gets a little bit funny, but electrons are virtually massless, okay? When we're talking about the mass of an entire atom, we only count the protons and neutrons. The electrons, although they have a mass, it's extremely, extremely small, and it's not really counted in the entire atom. Okay? So really, electrons are just, they're just a negative charge. Okay? And I know that's kind of funny to think about if we're, because we're thinking about classical mechanics, like things have a mass, right? This doesn't weigh very much, right here, this little thing, but this textbook weighs a lot. It weighs more. So if we think about two distinct things, we think that the masses just should be different. And technically they are, but because the mass of the protons and neutrons are so much bigger than the mass of the electron, we really don't consider the electrons as mass. And this gives way to quantum mechanics where electrons, like I say, are just a charge, and really electrons do some crazy things. They don't obey the laws of physics, really. That's why it's called quantum mechanics. There's some crazy stuff that happens there. It's almost like the electron can disappear and reappear somewhere else instantaneously, so it doesn't travel like a regular object either. Okay? So when you think about, if we think about the periodic table again here, the mass that you see, so let's say for carbon, right? Again, it's getting a bit messy there, sorry. But carbon, if we're talking about the mass of carbon, 12.011, or 12.0, what is it on yours? It's a little more accurate, a little more precise, 12.0107. That's the average atomic mass. We talked about isotopes last day. But this is just considering the average number of protons and neutrons in a carbon atom. It's not considering the electrons. Because if you think about it, in carbon there are 6 protons, 6 neutrons, and 6 electrons. So 12 is just the protons and neutrons, right? So we don't count the electrons as mass. All right, the next section in your notes talks about isotopes. So we did talk about this already. So I jump around from these notes a little bit because I just kind of can't contain myself. I'm so excited about chemistry, right? So we have talked about isotopes already, but here you go. Here's the official notes here. You can fill in the blanks. And this is what it is. Isotopes are atoms of an element that have different numbers of neutrons. Okay? And this makes the atom a little heavier or a little lighter than other atoms of the same element. I used the example the other day about us humans, right? Some of us weigh more than others. We're all still humans, but we have, some of us have a little extra maybe around the belly here, and some of us don't, right? And so we have different masses. Same for atoms of an element. Okay, atoms of carbon, as I show here in the example, okay, most atoms of carbon have 6 protons and 6 neutrons to have an atomic mass of 12 atomic mass units, 12 AMUs. So that's 6 from the protons and 6 from the neutrons. But an isotope, or another version of carbon, has 8 neutrons and 6 protons. Okay? So the protons are what's really important. That's what makes an atom, a certain element. Okay? And the neutrons, though, can be different. Okay? There can be more or less. So the one with 8 neutrons and 6 protons is called carbon-14. And you've maybe heard carbon-14 dating. Okay, you've heard things about carbon-14. It's an isotope of carbon. So carbon-12 is the most common. Now, the average atomic mass that I've talked about before is the weighted average of all known isotopes. The weighted average. Okay, so you can, the boldface terms should be your blanks there. You fill those in. If we go back to our periodic table, again, for carbon here, 12.0107. That's the average atomic mass. And all of these elements will have long decimals for average atomic mass, because that's taking into account all of the isotopes of carbon and their relative abundance. So because this number, the average, is so very close to 12 atomic mass units, that means that most of the atoms of carbon have a mass of 12 atomic mass units. That's 6 protons, 6 neutrons. Okay? Most of them. The vast majority, 98% of them. Okay? But there are some, there's a couple percent that are different masses. Carbon-14, carbon-12, carbon, 15, whatever it is. So they have different number of neutrons, but they're very small amounts of them. Okay? Up in the upper atmosphere, there's isotopes of carbon, that carbon gets blasted by the UV rays and stuff like that, and they change character and stuff. And so in the air we breathe and the carbon that our body is made of, we breathe in all these different isotopes. And that's sort of how they do carbon dating. There should be a certain percentage of carbon-14 atoms in a living being's body, because they're breathing in the air and all the average. They're breathing in the average. But after a while, after they're dead, they stop breathing in all these little isotopes, and eventually the isotopes kind of break down, and there's not as much of these isotopes, and so they can kind of take a sample of this living thing that's dead, this organic thing, and they can figure out how much carbon-14 is left, and then they can determine roughly how old something is. It only works up to about 6,000 years. The half-life, I think, is 5,700 years or so. So for carbon-14 to automatically break down to carbon-12, it takes 5,700 years. So they do the math, and they can figure out how long something's been dead, approximately. So that's kind of what carbon-14 dating is. It's not like when carbon-14 dates carbon-12 or anything. It's not like they get together and have a romantic episode or anything. It's not that, just in case you're wondering. So I'm sure that's what you were thinking, right? No, you weren't.
I don't.
You know what I'm talking. Okay, because I thought you might be confused. No, okay, good. All right. Yes, Sam would be the one that would not be confused about that. Yeah, he would be the one that wouldn't be. Okay, just bugging Sam. Okay. Any questions about isotopes or atoms dating other atoms? Any questions about that? No, we're good. Okay. All right. Okay, so next in your sheet, that's pretty much the end of your notes. We're going to do an average atomic mass example here. So I'm just going to show you how they come up with an average atomic mass, and you can break out your textbooks, and we'll take a look at a question from the textbook here now. So for this final example, again, in page 103, number 13, it's asking for silicon. What's the average atomic mass? It gives you, these are the relative abundances, right here, the percentages of each isotope, masses for each isotope. You take those masses, and you multiply by the decimal form of the percent. And you get these values over here. You add them up to get your final answer. And I wrote this answer with proper sig figs simply because there's 3 sig figs here, so that's the least number of sig figs. Okay? So you can take a look at this example again, and that's your example for average atomic mass.